Hello and welcome to Math IPREP Part 3. In Part 3, we're going to talk about lines, the linear equation, slope, y-intercepts, graphing lines, and the relationships that lines and their equations represent. So linear equations form a line when they're graphed, and they have a general format of y equals mx plus b, where m is the slope of the line. So that's going to kind of tell us how steep it is. The bigger m is, the more steep our line will be. And b is our y-intercept, and that is where the line meets the y-axis on the graph. So let's look at what these mean. So here we have a couple equations. We have y equals 0.04x plus 1. We have y equals 4x plus 2. And we have y equals 20x plus 30. So when we're looking at this, we can kind of break it down. So we know y equals mx plus b is our format, where m is equal to our slope, and b is equal to the y-intercept. So we see this first one has a slope of 0.04. We see that it's not a very steep line at all. If we compare it especially to these other two, this one has a slope of 4, and we see it's a little bit more steep. And this one has a slope of 20, and we see that it's very steep. And then we can look at the y-intercept. So on this one, it's 1. And remember that the y-intercept is the point that the line crosses over the y-axis. So on this one, it'll be right there, and that is a value of 1. Over here, we have a y-intercept of 2, and as you can see, it crosses at 2. And here, it has a value of 30, and as you can see, it crosses at 30. So even right away, if we didn't have these graphs drawn out for us, just by reading this equation, it can tell us a little bit about the line and what it does. So let's talk a little bit more about the slope. So the slope is the m in y equals mx plus b. This is a number that states how steep a line's incline is. So slope has an equation of y2 minus y1 over x2 minus x1, where x2, y2, and x1, y1 are points on the line. So really quick, I just want to show you guys what that means a little bit. So when we say x2, y2, and x1, y1, for example, if we had a point here, right, and we had a point here, this point over here would have the coordinates x2, because it's farther to the right, y2. And this point would have the coordinates x1, y1. All right? And then you use these 2 points to find the slope. So if we didn't have this equation right here, we could use these points to find the slope by taking our rise over run. So our y2 minus y1 over our x2 minus x1. So again, y2 minus y1 over x2 minus x1. And like I referenced a second ago, this is also called rise over run because it's kind of comparing how far up the line goes versus how far horizontally or over it goes. So how steep is your line? That's your slope. So let's compare some equations to each other and take some guesses about which slope is bigger. So in this first one, we have 2 equations. We have y equals 3x minus 2, and we have y equals 4x plus 5. Which of these has a bigger slope? If you said this one, you are correct, because 4 is bigger than 3. So therefore, this one has a bigger slope. What about this problem? Y equals x plus 5, or y equals 1/2 of x plus 23. Which one has a bigger slope? If you said this one, you are correct, because this one has a slope of 1, and this one has a slope of 1/2, and 1 is bigger than 1/2, right? Look at one more, and this one is going to be a graph, not an equation. So which one of these has a bigger slope? The one on the left or the one on the right? If you said the one on the left, you are correct, because this one, you can see if it goes over, it's also going up. So that shows some slope. This one is completely flat, right? So that means no matter how far over you go, it will never go up. So its slope is actually 0, right? So this one has a bigger slope. So now let's talk about some relationships that lines can have to each other. So we have two types of lines that we like to talk about. So the first is parallel lines. So these lines run next to each other, but they never touch. So like railroad tracks, right? You can go as far over to either direction as you could ever go, and they'll never ever cross. So this isn't the perfect example because this one's kind of slanted. I'm not great at drawing lines. There you go. But no matter how far over you go, those lines will never ever cross, right? Perpendicular lines cross at a right angle. So you're going to have one here, and it's going to form a 90-degree or a right angle. So how do you think that the slope of these compare? So when you look at these two parallel lines, what do you think their slopes are compared to each other? They have an identical slope, right? Because as you go over, neither of these lines are going up, right? So they both have a slope of 0. So parallel lines have identical slopes. How do you think that the slopes of perpendicular lines compare to each other? So these slopes are going to be the opposite reciprocal to each other. So in other words, if one of our slopes is, let's say, 2/3, our other slope is going to be -3/2. So you see how we switch these signs and we flip the numbers. Opposite reciprocal. Here are those lines kind of graphed out for you. So on the top, we have our perpendicular lines. So as you can see, we have our slopes in here, right? We have our red line, which has a slope of -1/8. And we have our blue line, which has a slope of +8. And then we look over here. We have our red and blue lines. Our red line has a slope of 8, and our blue line also has a slope of 8. So there is just kind of a little visual example for you to kind of compare the slopes of these two types of lines. So that is all for section 1 of part 3. So if you would like to take a quick break, maybe get some water, this is a good time to do that. Let's go ahead and pause and then come back whenever you're ready, and we'll start part 2. So this is going to be section 2 of part 3. And in this section, we're going to talk a little more about lines and specifically what lines represent. So lines explain a linear relationship between two variables. As one variable changes in value, the other changes as well. So kind of how we're talking about rise over run, right? So as it goes over, it also goes up or down. Or sometimes it doesn't do either, right? And that's when your slope is 0. But the rate that they change in respect to each other is the slope. So here's some examples. A line could explain the relationship between people and food at a party. So the more people you invite, the more food you need, right? And it could look something like this. So you have your people, you have food, right? So as more people, as you go to the right, those numbers get bigger, you get more people, you also need more food, which makes sense. You know, if you have more people they need to eat, you need more food. I could also explain the relationship between your age and how many times you have driven a car. So the older you are, the more times you have likely driven a car. So maybe this is when you turn 16, you've never driven, and you have your license, and now every year that you're driving, you are racking up number of times that you've driven your car. Right? So the older you are, the more you have driven your car, which would make sense as well, right? And so something to note about these two lines is we have our variables, right? We have food and people, we have your age and the number of times you've driven. So you might be wondering and ask, how do I know which variable to put on which line? And the way we'll do this is, first of all, let's identify these. So this line, our up and down line, is our y variable. And this line, our left to right line, is our x variable. So we have x and we have y. So the x value is going to be known as your independent variable. So kind of how the word implies, independent, it's all about itself. It doesn't really matter about other things. This number represents itself. So number of people, right? It doesn't matter how much food you have, right? The number of people will be the same. You could buy food for one person or for 20 people, but the number of people that actually end up coming to your party, that doesn't change based on the food, right? But then we have your y variable, which is your dependent variable. So your dependent variable depends on your independent. So in other words, as x, in our case, as x goes up, so does y. As we have more people, we need more food, right? Which makes sense. And it's the same down here. As our age goes up, our number of times driven goes up as well. And that's because the number of times you've driven depends on our age. Just like the amount of food we need depends on the number of people that come to our party. So let's try this out. So first we're going to read through, then we're going to identify which is our x and which is our y. Remember, our x is going to be our independent. And our y is going to be our dependent. Let's go ahead and read through this. So we're going to write an equation for the following situations. For every $6 that Billy gets an allowance, he can buy one dinosaur toy. So looking at this, which one depends on the other? Does the amount of dollars he have depend on the toy? Or does his ability to buy the toy depend on his money? And I would say it's probably that way, right? The dinosaur depends on the money, right? Here's your y. And here is your x. So for every $6, you can buy one dinosaur toy. So we know that all our equations should look something like this, right? Y equals mx plus b, right? So that's how our equation is supposed to look. We can put y equals, we know m here, and then x plus b. So in this case, if y equals one dinosaur toy, so y has a value of 1, how many x's do we need to equal 1 y? So how many dollars do we need to get one dinosaur toy? So we need $6, right? And if we need $6 to get one toy, that means a $1 bill has 1/6 the value of a dinosaur toy. So if y is equal to 1, if a dinosaur toy is equal to 1, then $1 is worth 1/6. And this can get a little confusing at first, but once you kind of analyze your equation, then it's not as bad. And I erased the y-intercept here, and that's just because in this case, we don't have one, right? We're not starting with any dollars. And that's kind of what we said, right? Y represents the toy, and X represents dollars. So Y is the toy with a value of 1, and X is $1, right? So if this was plus, let's say 3, that would mean that we have $3 already saved up. But that's not the case. Or sorry, that would mean we already have 3 dinosaur toys. I'm so sorry. Right? Because this would go plus 3. Because right now, if we have $6, right? So let's plug this in. If you really want to see if this works really good, let's plug it in, right? We have 1 y equals 1/6, and let's say we have $6, right? Of 6. What's 1/6 of 6? 1. So therefore that makes sense, right? If we have $6, we have 1 dinosaur toy. So if this said plus 3, that means we start with 3 dinosaur toys. But we don't, so there's no y-intercept. So it's just this. This is your final answer. Y equals 1/6 of x. So let's look at another one. And this one will actually be a little bit less confusing for a lot of you, but if it's not, don't worry at all. So for every day a homework assignment is late, you lose 5 points of the total 50 points of participation credit. So for every day a homework assignment is late, you lose 5 points of the total 50. So let's think about what that means. So for every day, so that tells us right now that day is our independent, right? Because they're saying for every day, you lose 5 points. So the amount of points that you lose depends on how many days it's late. So for every day a homework assignment is late, you lose 50 points of the total 50. So you already have 50, right? And then you just kind of have to put it together like we did with our last one, right? So if we know y is points, right? Y is points. We put y is equal to, and then what's our slope? So for every day, for every 1 day of x, how many points are we losing? 5. So for every 1 day that we're late, right? Every 1 day we're late, we lose 5 points. So if we're late 1 day, what's 5 times 1? 5, we lose 5 points. If it was 2 days late, what's 2 times 5? 10, we lose 10 points. So that's our slope. But we still have one more part of our problem, right? We have a total of 50 points that we start with. If we're late 0 days, we don't lose any points. But how many do we get? It says 50. So how do we make up for this? That is where our y-intercept is going to come in. Plus 50. We're already starting at 50, but then every day we're going to lose 5. All right. Let's go ahead and move on to the next slide. So again, we already have our equations. We just figured those out on our last slide. They're now displayed below for you guys. So now let's do a problem using our equations so we can really apply them. So Billy currently has $24 in his piggy bank. How many dinosaur toys can Billy buy? So try to think back. He has $24. Is this our X or our Y value? It's our X value, right? Because we know X is dollars. So we're gonna have Y is equal to 1/6 of 24. 1/6 of 24 is equal to 4. So if Billy has $24 in his piggy bank, he can buy 4 dinosaur toys. All right, so it's pretty cool how we can just take our equation, we can plug in what variable that we're given, and we can figure out how much of something else we have. So let's do it again with our homework example. So you turn in your assignment 3 days late. How many participation points can you receive? And remember, for every day that a homework assignment is late, you lose 5 points of the total 50. So is 5 points, is that going to be going to X or Y? Or I'm sorry, 5 points, we already figured that out, that's right here. For 3 days late, right? 3 days late, is that going to be X or Y? Is Y days or X days? It's X, right? So we talked about how Y is points, so X has to be days. And then we just have to solve. Y is equal to -5 times 3 plus 50, which is equal to -15 plus 50, which is equal to 35. So 35 points. All right, let's move on to the next one. So graphing a line. So a graph of a line allows you to visually represent a relationship. To graph a line, you will find a point to start at. This could be your X or your Y-intercept, which you already know, and Y equals mx plus b, or a point you know that the line crosses. So if it gives you a point in your question. So next, all you have to do is extend your line. So you can use a slope, which you know Y equals mx plus b, or if you're given a second point, you can dot that as well. And then you just have to connect your line and extend it. So when you have a line, make sure that all of your axes are labeled, so you know which is your x-axis and which is your y-axis. Remember, y goes up and down, x goes side to side, and make sure the equation of the line is written. Writing the coordinates for intercepts can make your line much more clear. So fitting a line to data. Not all relationships are linear. Sometimes there are other types of equations that better fit a relationship. So all the lines we've talked about, they go like this, right? They're just a straight line. But some lines look like this, some lines look like that, some lines look like that. There's just all kinds of lines that we can see. And all of those can be represented mathematically. So not all data will exactly fit a line. In a relationship between food and people at a party, it's possible that not every person comes as hungry as the next. So in this case, there's something called a scatter plot, right? In this case, you see there's not really a clear line that goes through all those points. But you can do something called a line of best fit, which kind of goes through as many as possible and maybe takes the average, right? It's your line of best fit. And that explains kind of a prediction of a relationship. So you could say that as there are more people, they will likely eat more, but it's not guaranteed, right? And so all of these dots here would be examples. So this could be a time that like 3 people came to a party and they had 1 bag of chips. Or this could be an example where 8 people came to a party and they used 8 bags of chips, right? It just really depends. We put all that together and we get our line of best fit. So thank you for watching Math IPREP Part 3. If you look below, there should be more videos that have some examples of everything we just talked about, including lines, the linear equation, finding slope, y-intercept, graphing lines, finding the relationships. We have all kinds of stuff, some good practice problems there, and that will just be in another video. Thanks for coming to Math IPREP. We hope you go on and watch Part 4, and if you haven't seen Parts 1 and 2, please do that as well. Thank you.